So welcome to Vladimir Vovk. Actually, Vladimir, I've done a bunch of these interviews, and you're the first person who I've not met yet. So this is very nice to meet you. And this is John Cherian with me, one of our grad students, our star grad students here at Stanford, who works with Emmanuel Candes and works on conformal inference. And he knows a lot more about it than me, so I thought he'd be a great person to have with me in the interview. So
nice meeting both of you. I know John's papers as well.
And you're in London, is that right?
That's right. It's not London. It's just outside the M25, almost in London.
So one of the reasons I haven't met you is we move in different circles. I'm a statistician. You're more of a, did you say engineer, electrical engineer or training?
No, it's not true. Formally, I'm a computer scientist, but I prefer just to work alone. So sometimes I talk to people on MS Teams. They tend to be maybe statisticians. Probably they're mostly statisticians.
So maybe just tell us a bit about yourself, your background to get started, where you came from and how you got into computer science, machine learning.
So I was born in Ukraine, but to get my university education, I moved to Moscow, to a very foreign place. So it was, I felt very uncomfortable for the first year, a different language, different environment. So my department, I started from a medical institute. So my plan was to do, I was interested in artificial intelligence. And they had a department doing, they called it biological cybernetics. But then it turned out it was also called medical cybernetics, and I decided it's not something I liked. So I quit, and I entered Moscow State University, this Department of Mechanics and Mathematics. And my department was mathematical logic. So this is my background. So essentially, I'm a logician. I'm not a statistician at all. So I'm foreign to statistics, and maybe it's something. And even my way of thinking about statistics is not very statistical. Probably it's something. It would. So I am still studying statistics. Okay, so probably that's it.
Yeah, I read somewhere that you knew Kolmogorov, or you were his student, or?
Well, I was his student, and this is why. Okay, so this is why I went to the Department of Mathematical Logic, because he founded, I think he founded the Department of Probability in Moscow State University, and then he founded the Department of Statistics. But at some point, there was no chair for the Department of Mathematical Logic, so he moved there. So we came simultaneously, Kolmogorov and I, to the Department of Mathematical Logic at very different levels, of course. So he came as the head of the department, and I came as a student. So I listened to some talk by Kolmogorov to students. Maybe it was just for students in mathematical logic. And then it was about Kolmogorov complexity, about randomness. So of course he was interested in Kolmogorov complexity, I think, just because of its applications in algorithmic randomness. And I thought it was fascinating. So I decided this was something I want to do. I even saw some connections with artificial intelligence. So it was not something, it was just my childhood dream to do something about artificial intelligence. And then but actually it was somebody else. So now he is Kolmogorov's successor. He's the head of the Department of Mathematical Logic, Alexei Semenov. At that time, he was working with Kolmogorov, and he offered to me to become Kolmogorov's student. So this is how I became his student. So I was his student for 3 years in my undergraduate studies, and for another 4 years as a PhD student, but I didn't see him often when I was a PhD student. So my main discussions with Kolmogorov were while I was still doing my undergraduate studies.
So tell us about what we now call conformal prediction, how it started.
In my mind, it started from Kolmogorov. And also Vapnik was very influential, but in some indirect ways. So for Kolmogorov, for him, a big question was, how do you define randomness? This is what my compatriot, Richard von Mises, who was an Austrian, but he was born in Lviv, what is now Lviv in Ukraine. It was Lemberg for him. He designed some foundations of probability based on collectives. But of course, Kolmogorov's foundations of probability, they became dominant, and everybody was convinced that Kolmogorov's foundations is the right way, except for Kolmogorov. And Kolmogorov decided that he wanted to make von Mises' collectives more down to earth. Because for Kolmogorov, infinite sequences didn't exist. I mean, they didn't exist empirically. You can't see them around you. So he was interested in finite sequences, unlike von Mises. So he defined what I believe as the notion of exchangeability for finite sequences. And then if you want to predict something under the assumption of exchangeability, I think it's something I learned from Vapnik, how important it was. Because for Vapnik, his whole world was inside this assumption. And when you want to predict something, how do you do it? Suppose you have some training set, and you have a new object like X, and you want to label it. How do you do it? I thought maybe you should try all possible labels for this object, and then you compute the randomness deficiency, the deficiency of exchangeability for this whole thing. And then if this deficiency of exchangeability is high, it doesn't look exchangeable. So the new label is strange. Then you can discard it. It's an unlikely label. And if it's not large, then you don't discard it, and you get some prediction set in classification or regression. So it's an ideal picture. Of course, you can't compute exchangeability deficiency, but you can have some approximations. And so it's, by the way, you mentioned a date, 1998. I don't think I agree with this date. I've seen it, but it's not about conformal prediction. In my mind, conformal prediction, it's always about p-values. When you do something else, it's not a conformal prediction. Like p-values, they're good because when you do it online, p-values will be independent. And I think it's the right thing to use in conformal prediction in any case. But in 1998, we used e-values, not p-values. So e-values, they are becoming popular now, I think. More popular than, they have always been popular in the algorithmic theory of randomness, but not in statistics. For some reasons I never understood, statisticians never liked and used e-values.
But at the same
they
time,
used p-values a lot.
well, p-values are also losing popularity too in many areas.
That's right, and lots of people are saying that e-values is the right way to do it. But p-values, I think they have their right place, and at least for me, one prominent place where, in my mind, maybe it's not so prominent objectively, but in my mind, p-values are the right tool in conformal prediction. It might change. I've been trying, I was trying like a year ago, for example, again, to try and apply e-values in conformal prediction, but I don't think I succeeded. It's something still, p-values have lots of advantages in conformal prediction.
So I guess maybe following up on this question of what delineates conformal prediction to you, you mentioned p-values. Obviously, as the field has gotten more popular in statistics, there are a lot of non-parametric or distribution-free methods now that today get called conformal methods. What do you think about this trend? And do you think there should be sort of boundaries in what we call conformal prediction methods versus just maybe distribution-free methods? And where do you think that boundary lies? Is it that I have to be able to invert the procedure to get a test or to get a p-value or a valid p-value? Or what do you think maybe defines conformal?
I'm not sure. It's a difficult question for me. So I know there is, for example, conformal risk control. But my impression is really conformal. So it's something, so sometimes people are talking about, I don't know, learn then test. It's not conformal prediction, it's something different. It has two parameters. Probably it's essential for conformal prediction to have one parameter, maybe some threshold for p-values. When it's two parameters, when it's a pack type thing, if you want to have, if you have epsilon and delta, some probably approximately. If you have these two parameters, probably parameter and approximately parameter, probably it's not so much about conformal. I never called it conformal prediction. But it's difficult for me to tell where the boundary should be. Of course, I'm happy people call different kinds of things conformal. I have no objections to it. And conformal is not my word. We use some very awkward term. It was, I think, transductive confidence machines. And it was awkward because I think it was not even correct. It corresponded to what Vapnik called transduction in his books. But I think it's not the kind of transduction. Sometimes when people talk about transduction, they mean that you have a test set, an unlabeled test set, and you do its labeling in one go. So that not one by one, but in one go. So that kind of transduction, it's also important, and it would be good to use the word transduction in this context. So yes, I like conformal prediction, but it was suggested by Glenn Schaefer when we were writing our 2005 book.
Sorry, Larry Wasserman was I was one of his co-advisors at Toronto, so he's been a long time friend and collaborator. And I think he gets a lot. He and G get a lot of credit for informing the statistical community about conformal prediction. Isn't that true?
Of course, it's true. They were crucial in conformal prediction becoming popular. They advertised it. They proved very beautiful theorems about the efficiency. It was asymptotic efficiency of conformal prediction. So there are two sides for conformal prediction. A validity, which usually we want to have a small sample validity, versions of validity. But for efficiency, it's very difficult to prove a conformal predictor is efficient. So they proved asymptotic results about efficiency. Lee also designed an efficient full conformal predictor built on top of the lasso, which I found extremely impressive. It was of course, in our book, we did only some toy cases like least squares, ridge regression, but he did for a more complicated algorithm. And also for Larry Wasserman, so he designed, I think what is important, I think it's a research program which has been underexplored. So in the second edition of our book, so it was published in 2022, we call it the Burnaev-Wasserman program. So I learned about it from Evgeny Burnaev in Russia when I was visiting Russia. And actually it was in Kolmogorov's house, which is strange. So Albert Shiryaev organized some excursion to Kolmogorov's house. And there Evgeny told me about this Burnaev-Wasserman program. But it was also, later I found it in Larry Wasserman's papers. I never met him. But I corresponded with him. And the program is that it's kind of efficiency of conformal predictors. How do you find? So you start from some narrow, or maybe from some Bayesian model. And then you check the efficiency of conformal prediction as a method on this Bayesian model. It can be a Bayesian model, or it can be a narrow, some parametric statistical model. So how do you check it? So if you suppose we are talking about a Bayesian model, The best predictor is the Bayesian predictor. It's the optimal predictor in lots of different senses. But you might not quite trust this Bayesian assumption. So maybe you want to ensure against this assumption being wrong. So what you might want to do, you might turn this Bayesian predictor into a nonconformity measure. And then you build a conformal predictor on top of it. But then you'll inevitably lose. So you become more robust because your validity now is just under exchangeability. But you will lose something in efficiency. You inevitably lose. How much do you lose? So it's Bunai Wasserman's research program. So for all kinds of machine learning algorithms, you can ask this question: how much do you lose? But there is also one element of this program that is just Larry Wasserman's. It was not in Buzhnaev's version. So if you lose a lot, maybe it means that your original Bayesian algorithm, for example, Bayesian algorithm, was very fragile. Maybe you should not be using it anyway, because you lose so much when you make it robust. I'm sure there are some interesting examples of this program, interesting counterexamples, but I would love it to be explored further. Maybe we need some boundary, when it works, when it doesn't work. But the program itself, I find it fascinating.
Interesting, yeah.
So I guess, I mean, you've kind of touched on one important current research area in conformal prediction with, we mentioned efficiency or prediction set size. And I was wondering if you could talk a little bit more about what you think are exciting future directions in the field, whether they're about efficiency or coverage guarantees. What do you think is some of the most important issues facing the subfield?
Yeah, so I'm not sure I'm the right person to talk about it. So in 2022, our second edition was published. And after that, I switched to other things. I've been thinking about, I don't know, like diachronic Bayesian theory. How do you revise Bayesian beliefs when you don't want to do Bayesian conditioning? Bayesian conditioning, I think it's very, very restrictive. Okay, so but I'm very much interested in conformal prediction again. So I would like to understand conformal risk control, for example. The new methods work about efficiency, but it's still, I need to do my homework for this. But in general, what I said about this Buzhnaev Wasserman program, I think it's a great direction of research. So it's applicable to lots of different algorithms. So it's also about efficiency. You can, of course, usually, it was shown in Lee and Wasserman's papers, in some other, in many late papers, you get asymptotic efficiency at infinity, which is not surprising. There are lots of results in statistics showing that you achieve all kinds of good things asymptotically at infinity. And somehow, in many cases, I don't know, somehow it looks very connected to the foundations of probability. Things like the continuity of probability, like Kolmogorov's axioms. You assume sigma additivity, and lots of people didn't want to assume it. And it so much depends on it. So in some cases, it seems to me as if when you read the proof, it looks as if, yes, it holds for finite sample spaces when you repeat some finite experiment many times. And then you just use those axioms to demonstrate that the general case is similar to this finite case. And you could never disentangle. You don't know when this infinity comes. It's still, yes, you get something at infinity. So I would like to have something more down to earth. And the Buzhnaev-Wasserman program, it might be the right way out, because you have this Bayesian algorithm. Or it can be the Gauss linear model, for example. It doesn't have to be Bayesian. It might have some parameters. And then you have this model. And in this model, you can do something much more specific. It doesn't have to be just at infinity. You can do some more tangible things. Yeah, so I can't say much about it. Probably that's all I could say on this topic.
When I first learned about conformal prediction from my son Ryan, who I think you know, he's also worked in the area. And when I explained the basic idea, it was so simple. I was thinking to myself, I mean, permutation tests were invented in the 1930s. Why did it take so long for the community to think of this? I mean, it was 60 years later or something, or many years later. Seems like a very simple idea, but somehow it was under the radar of everyone.
It's very surprising. I think it was like in 1999, about this time. I was sure conformal prediction is something well known in statistics. I searched literature. I did this extensive literature search, and I didn't find anything. The closest thing, of course, it was, I think, tolerance intervals. There's expectation tolerance intervals. But they did it in a 1D case. And I looked at how they extended it to the multidimensional case. They did some very ingenious but very complicated things. They didn't do. It seems what they could do, you just apply some non-conformity measure, you get a 1D thing, 1D data set after that, and then you apply a tolerance interval to this set. They didn't do it. And what we call inductive conformal prediction, what is usually called split conformal prediction. So that's a very slight variation on tolerance regions. You just make it conditional on some learned model. So you have a machine learning model, I don't know, a large language model, and then you have this prediction rule. And then you apply, you do this tolerance prediction on top of it. And this is split conformal prediction, so it's very similar. Yes, I agree.
So conformal predictions had many also important real applications. And to put John on the spot for a sec, John's done some very nice work with the Washington Post applying conformal prediction. Maybe I don't know if you're aware of it, but you want to just say that?
Of course.
Yes, I mean we've used some conformal methods for essentially prediction sets for election outcomes, and we'll see it again this fall in November. But when you think about sort of modern applications of conformal prediction, are there any that you're particularly excited about, or areas you think are particularly promising for it?
Oh, this application looks most impressive to me. Of course, when you learned about it for the first time. So yes, it was amazing. So my colleague Alex Gamerman even tried, I know, to convince Financial Times to use something like this for predicting British elections. I'm not sure what's the state of this. Probably it's too late for our current elections, so they're coming in a few weeks' time. But yes, it's amazing. And of course, we don't have exchangeability, as you explain in your papers, and you had to do something about it. So, yes, and you did all kinds of tricks, and the US is a big country. The UK is not so big. It's just one time zone, so it should be easy. It's slightly more exchangeable, but still lots of non-exchangeability. Yes, it's an amazing case study. I agree.
So I think, I mean, maybe following up on this question of applying conformal prediction today and sort of deviations from exchangeability, right? We derive these very nice finite sample guarantees under, what seem to maybe the outside observer as maybe hard to parse, but fairly strong assumptions of exchangeability. And when you mentioned large language models, for example, it seems like a lot of modern machine learning, not just in the election setting, works with not just non-exchangeable data, but unstructured data with unstructured labels. How do you think conformal prediction can be adapted for these contemporary use cases? And what do you think the path forward is for a conformal prediction?
A short answer is I don't know. I started reading about conformal prediction for large language models a week ago, and I've been very busy with other things, so I don't know much about it. But what I found unsatisfactory with large language models is that it's not about, they don't have a notion of ground truth. It has to be, it's something, you have to bring it from outside. So there is this retrieval augmented, what was that? Okay, so this retrieval augmented version of large language model, but you add something to it. Generation, I think it was. Conformal prediction is another way to bring ground truth into it. So that it should not be just about the language. Different people are saying, are telling different things about the role of the language in their thought. I think in my thought, it's minimal. I'm thinking, I don't know, in images, in formulas. It's not about the language. But large language models, yes, they look as if they can think, but they're not thinking. They're processing a text. And how do you bring so like Paris as the capital of France? It's a fact of the English language. It's not a fact about maps, about the earth. It's all about English language. So I don't. So yes, I would be very much interested in understanding how you can bring. In what way would be the most efficient. And I very much hope conformal prediction would be useful in this respect as a source of ground truth for large language models.
Maybe that's a good place to stop. It's been really enjoyable talking to you, Vladimir. Thank you for doing this. And I think
Thank you very much.
the audience will enjoy hearing conversation.
Thank you for inviting me.